Hey guys, welcome back. This is start of a new topic. We're done with gravitation mostly. Discussed some problems with some students day before yesterday. I have the video. I didn't upload it. I'll see if I have to upload it. I'll upload it. So let's start talk about the topic of oscillations or simple harmonic motion. SHM. SHM is called as simple harmonic motion or simple harmonic oscillations. Also, we will talk about them in this topic. But before getting to SHM, before we talk about simple harmonic motion, what is an oscillation? That is what we need to talk about. Anybody has any answer? Like, what do you call an
Yes, sir.
oscillation?
So I have an answer.
Yeah, speak up.
Like
Sir,
we can,
to and
in
from
terms of
motion from a
pendulum, we
point.
can say like time for 1 hour.
One person at once. What were you saying?
Sir, Aditya, sir,
Yeah.
I'm saying that in terms of pendulum, we can say like the time taken for this bob to cover one from one extreme post to another extreme post,
I'm
sir,
Sir,
not
can I
talking
say?
about any
or we can say
definition.
recurring again.
What is
Sir,
an
in
oscillation?
general, to and from motion from one point back to the point.
Yeah, so to talk about a thing called oscillation, oscillation is a thing where a body is moving to and fro. This is what we call it as an oscillation, as simple as that, or just simple to and fro motion. Okay. Now, if there is a body, there is a point, it goes to one point, it comes back, it goes to another point, it comes back. If this is happening, you can call this as an oscillation. We refine this thing down to some more point, but to at this point, any body which is going in to and fro motion can be called as an oscillation. There is no rule or there is nothing like that to call it as an oscillation. Okay, just a to and fro motion is more than enough for a body to call it as an oscillation. Now, there is a word called periodic motion. What is a periodic motion?
So
Where
the
it will
time period
repeat
is the
after
same.
some time, sir.
Time period is same.
Yes, sir.
After
Every
some
time.
after some time that same motion will happen in that system.
Again and
Exactly.
again.
Repeated in
To,
equal
to,
intervals.
to speak about periodic motion, it has to repeat itself. It has to repeat itself after a
After a
specific
few
interval
times.
of time.
Yes,
So
sir.
you might have come across the topics, functions called periodic functions already, right? Didn't you?
Yes,
Yes,
sir.
sir.
Yeah, you
Yes,
might have
sir.
come across
Yes,
the
sir.
ideas called periodic functions, which they repeat themselves after a specific interval. Periodic motion is also motion where it repeats itself. The way it moves, it simply repeats itself after a specific interval. Now, my
Excuse me,
question
sir.
is, yeah,
So if it repeats itself in like alternate intervals.
then let us say it is repeating itself after 2 seconds and 3 seconds and 2 seconds and 3 seconds. Let's just say, is that what you're asking?
Yes, sir.
Then the
Yes,
time
sir.
period is 5 seconds. So you don't call it as 2 seconds and 3 seconds. The time period is 5 seconds. That's all. So it's clearly
Okay,
repeating
sir.
itself after 5 seconds, right?
Oh, okay, sir.
That is how you say it. Now, my question is every oscillation a periodic motion? Is every oscillation a periodic
Not, sir.
motion? No.
Not
No,
No,
necessary,
sir.
sir.
not
Uh, an
necessarily.
Not
oscillation can be an
necessarily.
oscillation. It simply has some position. It is going and stopping, let's just say, and came back. And it's going again and stopped at some other point for some other time and go back. But the thing is, it is just moving front and back. So you can call it as an oscillatory motion, but it doesn't have to be periodic motion. Now, my other question is every periodic motion is every periodic motion an oscillatory motion?
Yes, sir.
Yes, sir.
Yes, sir.
What? Is
Yes,
every
sir.
periodic motion an oscillatory motion?
There can't be an
No,
exception to
sir.
this, sir.
No, sir. Like for circular motion, which has uniform
Exactly.
speed.
So, guys, they are not of the same kind, or they have interrelated or anything like that. A oscillatory motion is an oscillatory motion. It has nothing to do with periodic motion. Let's just say there are like some properties of a motion. You can call it periodic, you can call it oscillatory. They can combinedly exist, they can separately also exist. Okay, oscillatory motion is just simple to and fro. It doesn't have to be periodic. there are periodic motions also. Now, periodic motion is something it repeats itself, something that repeats itself. But all the periodic motions don't have to be oscillatory. Take a circular motion. Take a circular motion. It is clearly starting here after specific interval. It is clearly repeating itself. Take an elliptical motion in the gravitation. It's starting at this point. It's definitely repeating this motion. All these motions are definitely periodic, but they're not oscillatory. They're not oscillating. They're going around. So you don't really call it a oscillatory motion, but periodic. Now, can somebody tell me a motion which belongs to both oscillatory and a periodic motion?
Pendulum, sir.
A pendulum.
The
Yes,
Newton's
that's good.
cradle.
A pendulum. That is a good answer. Yes. Anybody else?
The Newton's cradle.
Newton's cradle. What is Newton's cradle?
Like that, there will be a set of bobs touching to each other, and that one bob is really
That
that
is basically a
at the extreme
pendulum
most
only.
it will.
So even when a ball is
Yes.
going up and down
Yeah.
on a surface that's like from high to low and then again up.
Again, come again.
So like there's a curved surface and a ball is going up and down on that.
Oh, that's a good idea, right? So the body is moving like this. So clearly an oscillatory motion. Yes.
So
And
someone jumping on a trampoline.
Tuning fork, sir.
Oscillatory motion clearly, and it is periodic also because it is repeating itself after specific interval of time. It is going there, coming back, and then going there, coming back. So it's clearly repeating itself. So it is both oscillatory and both periodic. Now, some other example somebody gave.
Tuning.
A tuning fork. Sai Vamshi says you hit it. There is a tuning fork. Let's just say you hit it, it oscillates. A tuning fork, the hand oscillates clearly. Now the oscillation of the hand is clearly oscillatory. Obviously, that is why you call it as an oscillatory motion, and obviously it is also periodic, strictly speaking. But in
The
reality,
spring-
they are not really periodic. They kind of slow down after some time and they die down. So we are not talking about the reality cases. Even in a pendulum,
Sir, a ball which is bouncing off a floor which has no friction without air friction.
okay. Even in the case
So the
of a
spring
pendulum,
also.
what? Yes, that's a good
spring, sir.
idea. A spring block system, which is oscillation, which is in the motion, oscillatory motion, and which is in oscillatory motion, and it is also
Periodic.
periodic. Clearly, it is repeating. Now, guys, I'm repeating it again. We are not considering any losses. Every system that we are considering here is a lossless system. There is no friction. If there is friction, we will talk about them later at the end of this topic called as damped oscillations. We will talk about them where they're really difficult to talk. Okay, we can't really talk about them right now because the time periods change, everything changes. You clearly can see, like, you hit a tuning fork, it won't stay there for, it won't last forever, right? It eventually slows down. You have a simple pendulum, you leave it, it oscillates and it slows, after some time it dies down. That is because of the frictional losses. That is because of all the losses, all the non-conservative forces. We don't really consider that in this topic. We consider there is no losses. So all these motions that we just talked about, oscillatory and periodic. But please remember, somebody is texting yo. No. Oh, he's talking about a yo-yo. Mayur is saying a yo-yo. Can you people agree on that? Is a yo-yo periodic and oscillatory?
Yes, sir, because it comes back again.
Okay, so you agree that it is oscillatory and it also goes as a periodic motion?
No, sir,
Not
it
sure
depends
about
on how
periodic,
we
sir,
It's
but
upon us,
oscillatory.
apply
like
the
it's
force.
upon us.
It depends,
depends on how we apply
it
the
depends
force.
on a lot of situations because the person.
So
who's
one small
saying it-
doubt.
Yeah.
So is it necessary that the particle should come back with the same path as it went?
If it doesn't, then you don't call it as a oscillatory motion, right?
If it's going and coming to the same point, sir, just after every
Yeah.
time.
Let us say it started here, it went like this, came back like this. It's not an oscillatory motion. You don't call this an oscillatory motion, right?
Okay, sir.
Because it's not exactly to and fro. It went in this path. It has to come back in this path. Then that is when you call it as an oscillatory. It's a to and fro motion. This is not to and fro. This is like a detour or a circular motion or an elliptical path. No, you do not call this as a oscillatory motion. Okay.
Okay, sir.
Now, so yeah, all the examples that you gave me, a pendulum, good for oscillatory and periodic, a tuning fork, oscillatory and periodic, a spring block system, an oscillatory and periodic, a ball in a pit, let's just say oscillatory and periodic. There are motions, only they are periodic for sure, but not oscillatory. There are motions just oscillatory, they're not periodic, they could be. Okay. uh, a question to you people. By the end of this topic, you people tell me, is a bouncing ball, these people are asking already, is a bouncing ball, is it, let's just say the coefficient of restitution is 1 only, so if it is bouncing, it is actually going back to its original height only. Let's just say it started here, bouncing and going back to the same height only, so it's constantly bouncing. Can we call this as an oscillatory motion?
Yes, sir.
Yes, sir.
And can we call this as a periodic motion?
Yes, sir.
No, don't just nod yes. Look deep
Sir,
into
it
the
is
definitions.
periodic, sir.
Look deep into the definitions. Look properly into the definitions. Then only make a call. You can't just randomly say that they are periodic or oscillatory. Look into the topic properly and then only make a call. Otherwise, you can't just say simply like that. Okay. Yeah. So that is it. Somebody is asking, sir, is an oscillatory, but okay, people are giving different answers. Now think about it, think about the definitions and then answer. I don't want the answer right now, you can answer me later also. A bouncing ball, is it a just an oscillatory motion or a periodic and oscillatory motion, or is it not both? It can't be both also, there's a case. So look into the problem and let's talk about it later. No, can you give me more examples?
Sir, rotatory B.
Rotatory,
B means in circus it there'll be no, sir.
there is a what?
Rotatory B, sir. In a exhibition they'll keep, no, sir.
Rotatory B, I don't understand what that means. Rotatory B, how does it look like? No, I don't get you. Let's get back to the point. Okay, somebody is asking, what about heartbeat? Heartbeat is periodic for sure, but your heart is not really oscillating anywhere, right? So you can't really say
So
if
it's
it is.
not periodic exactly. Sometimes it's fast, sometimes slow.
Yeah, then you can say the period is increasing and period is decreasing. Oh, somebody sent me this B thing. Acha. Leave it, forget it. It's way too complicated to discuss, Vamshi. So leave that part. Liquid in a YouTube. Okay, somebody gave another example. Good. You people are coming with some good examples. There's a YouTube. We'll actually talk about all these things in this topic. The screen share has stopped. Wait a second. This is happening little too frequent now. So Yashwant Kumar says, in a tube, if I fill it with some liquid, and we press it and leave it, it oscillates in the tube itself. The liquid oscillates like this. So that is a oscillatory motion and periodic, considering there is no friction at all. Okay. Now enough with the examples. Let's talk about the serious business in this topic. Yes, yeah, you being kids gave me a lot of examples for periodic motions, for oscillatory motions. Let us talk the big man's business in this topic. For a body to oscillate, what's the most important thing for a body to oscillate? Oscillate means if a body is going that way, it has to stop, it has to come back. So what's the most important thing? Sharath is
Conservative
saying
force, sir.
force. Conservative force, that's a good statement, but I'm not sure you don't really understand the weight of that statement that you just made. You just said we need a conservative force, okay, but let's look into it. Force is required, but what kind of a force is what is the nature of that force? Charan is saying there shouldn't be any friction. Yes, so there shouldn't be any friction. So since we considered conservative force only, that's a good thing. But you can call it in a much better way. Like, what kind of force do we need? What is the force exactly doing? Anybody, like, what is this force doing? What is its part in doing? Like, at least let's say a body is going in this direction. What's the direction of force that should be acting on it?
Opposite direction, sir.
Opposite direction, that is good. Opposite direction, that is one thing. Yashwant already made that, I mean, he already gave the answer. Yashwant Kumar,
So the force keeps opposing the motion. That's it.
That's a
Whichever
good
direction it
statement,
goes.
Aniket. Yes. So if the body is going this way, the force is opposing this way. If the body is going this way, the force is coming acting this way back. So that it's always acting towards somewhere around this region. It is trying to pull the body back to its original thing. Okay. You're trying to understand what I'm trying to say. There should always be a force for an oscillation to exist. There should always be a force which always should bring it back. If it is going, you should bring it back. If it is going, you should always bring it back. If only a body is going that way and the force is also acting that way, the body will never come back. It will just accelerate that way. So this cannot happen. The only possible case for an oscillation is this. So there is this word which is really important. Already this guy made the statement. So gave the word. It is restoring its original position. Restoring is the word, guys. Remember this thing. It is the most important word when it comes to this topic. The restoring force is the thing that is most important when it comes to topic. Because if there is no such thing as a restoring force, there is no such thing as oscillation. Let's go back and look into all the things. Let's start with the easiest oscillation. In this thing only, when the ball is going up, it is a gravity which is trying to restore. When the ball is going this way, the gravity is trying to restore its position. Same with the pendulum. If it is this way, the gravity component will act this way. If it is this way, the gravity will component will act. Try to bring it in the towards back. In this tuning fork thing, whenever you disturb it, it is a rigidity always tries to bring the body. I disturb the body, the rigidity of the body always trying to bring the body back to its original position. So that is called as a restoring force or a restoring torque. Even you can call it as a torque. But there is always, like, let us take a spring block system. If the spring goes that way, kx acts this way. If the spring compresses in this direction, the kx acts back. So even in a spring case also, like, you try to expand it, spring tries to bring it back. If you try to compress it, spring tries to bring it back. So you understand how a force is acting as a restoring force. That is an important case, guys. Is there any doubt? Is work done always negative, sir? Not exactly, Sumant. We will talk about the works done. We will talk about the momentums. We will talk about all the things. But let's just talk about the force at this point. Okay. So that is the most important thing, guys. You can discuss in other bodies also. Can somebody describe where is the restoring force in this case, where there is a liquid? Who is causing the restoring force? Anybody? No answer? Yeah, Aditya.
Is it buoyancy?
Not buoyancy. You don't know anything about buoyancy. So when the liquid is when they are at the same level, nothing will happen. But when the liquid is disturbed, it is simply this additional
Are
liquid.
these pressures?
What? No, a pressure or
That
anything,
pressure.
you in your terms, like in the terms that you can understand, you can simply say that this additional weight will try to push it back. So there is a restoring force there also. So the idea of restoring force is the most important thing, guys. Like every time you look at a problem, every time you look at a restoring force case, every time there is an oscillation, that important. If you are dealing with a question from simple harmonic motion, if you are dealing with a question in the oscillations, the first thing that you should be looking at is where is the restoring force. Okay. Let me ask a simple question. I'm not sure if you'd understand this. When we are speaking, when I'm speaking, my vocal cords making vibrations. Those vibrations are going into air. So all the air layers are vibrating. So all the layers in the air are basically oscillating. Who is creating the restoring force for the air layers? Who is creating the restoring force for the air layers? They are oscillating clearly. When there is a sound, the air layers, all the layers in the atmosphere or the region definitely oscillate. Who is giving the restoring force for them? No, it's not air friction. No, it's not inertia. Is it SHM? I don't know. You nobody's giving me the answer. Who is giving it the restoring force? Nobody gave me the answer. Okay, that's totally fine. But remember, guys, remember the point that there is always a restoring force. We will slowly learn how to look for the restoring force. Not right now. Maybe it's not possible for you right now, but we will definitely learn to look at the restoring force all the time. Okay, Sumant, what is it? You have a doubt? No. Guys, don't just use every word that you know. Please remember this point only, that whenever there is an oscillation, there is always a restoring force. Whenever there is an oscillation, there is always a restoring force. So that is the most important point in when it comes to the topic of oscillations. Let me just give you some random statements, some random situations where we will come across this thing. Take Earth, make a tunnel, dig a tunnel across the Earth's diameter. Leave a body here. It will go, stop here, it will come back, stop here. It simply clearly oscillates across the tunnel. Who is creating the restoring force, guys? In this case, who is creating the restoring force? Oh, there are a lot of people raise their hands. Okay.
Sir, gravity.
Gravity, sir.
Exactly, the gravity. When the body is here, gravity is acting this way. When the body is here, the gravity acts this way. So the gravity itself, of course, it varies for sure, but it is creating always a restoring force for the body to oscillate across. Take
Excuse me, sir.
yeah,
Sir, for tuning force, who is creating the force?
the rigidity. The rigidity. We will talk about these forces in the properties of material and all. Okay.
Okay,
We'll
sir.
talk about that later, not right now. The oscillations are created by the rigidity in the material. We will talk about it. Now, let me. I was saying something. I forgot. Yeah. Take a simple question like a simple ring, capital mass, and a small mass placed on the axis. It was clearly get attracted towards this position, but by the time it gets there, it comes back. So it simply oscillates along this point. Who is creating the restoring force here again?
Gravitational field, sir.
Again, so the not gravitational field, you can simply say the gravitational force itself, the gmm by whatever the force value we have, r square plus d square whole cube or something like that, right? We have this value. It is exactly creating the restoring force. So always the first important thing when you have a problem in oscillations, the first thing that you need to do is identify the restoring force. For a body to oscillate, there should always be a restoring force. Now, coming back to that point, so whenever there is an oscillation, let us bring in some new words called mean. There is a position called mean about which the oscillation is going. It goes from this point, comes back to this point, goes away, comes back to this point.
Between the extremes, sir.
Between the extremes, there's a point called mean. We will slowly get into this topic. Now, whenever it is on the right side, the body is on the right side of the mean, the force acts towards the mean. Whenever the body is on the left side, again the force acts towards the mean. So this is the important thing. The force always acts towards the mean only. The force always acts towards the mean only. That is an important point. But in that a special case, and that special case is where we are going to strictly put our effort completely, is let us always take a mean position. If you are at a distance x from the mean position, the force acting on you, if it is proportional to x, people put a minus here indicating that it is acting in the opposite direction. Since x is like this, force is in the opposite direction, they tend to put this minus there. If the force is proportional to the distance it is from the mean portion. If it is far away from the mean portion, the force is also heavy. If it is close, if it is very close, the force is less. But as it is going farther, the force is also getting heavier. That is the meaning. And it is also exactly proportional to x, because there could be cases where the force is proportional to minus x power 5, minus x power 7, x power 10, x power 11, whatever it is. We are not talking about any of the cases. We are bringing a special case, a simple special case where the force is only proportional to minus x. I'm repeating, the minus is simply indicating that the force is towards the mean, or it's a restoring force. Whenever you see a force which is proportional to minus, you're simply talking about a restoring force. If it is like this, then you call it as a simple harmonic motion. So guys, are all the oscillatory periodic motions are simple harmonic? No. There could be thousands of oscillatory motions. There could be tons and tons of oscillatory motions. Like I said, a ring, a mass system can be oscillatory. But we are not sure if the force is proportional to x. If it is proportional, yes. But I don't think it is, right? Because force value is gmd by root over. If it is x, it is x, right? Gmx by root over x square plus r square whole cube. How, on what?
Sir, if it's not proportional, so similar effect only, right?
Yeah, there will be oscillation for sure. There will be oscillations even if it is
Time
not
period
proportional.
also, sir, same.
If let me write, let me put a minus there. I'm putting a minus there, indicating that the force is in the opposite direction. The force can be like proportional to minus x cube. It can be minus x power 5. It can be like any way. There are always oscillations like this. There are always oscillations like this. But if it is not this, clearly it is not this, because here the force is this. So we cannot call this as an SHM. No, this is not an SHM. The only cases, there are some cases, we will look into these cases. There are some cases where force is exactly proportional to minus x is called as SHMs. So there could be oscillations. There could be different ways of oscillations like that you see on the right side. But not all oscillations are simple harmonic motions. You can only call a simple harmonic motion an SHM when the force is proportional to minus x. This is the only case where you can call it as an SHM.
Excuse me, sir.
Yes.
Sir, for oscillation, is it necessary the force should always be acting? Or maybe it just acts after a point?
I think it is necessary because the body needs to come back, don't you think? I mean,
Yes, sir. So after a point, it acts
what you're
again.
thinking is it can act up to some point and it can disappear and then act on the other side. Is
Yes,
that what
sir.
you're trying to say? Yes.
Yes, sir. And it keeps coming back.
Yeah. It can. There is a chance. Like I'm talking about another oscillation where, yeah. Why don't we take a hollow sphere of some thickness? Okay, and I make a tunnel across. Are you getting, Aniket?
Yes, sir.
So here there will be force, there will be force. From this point to this point, there won't be any force. So the body travels with a constant velocity here. From this point, decelerates, comes back, accelerates. So there will be acceleration, deceleration, then constant velocity, acceleration, deceleration, sorry, and constant velocity. So yeah, this is also an oscillation. It doesn't have to be, you don't really not call it as an oscillation. You can call it as an oscillation. Okay. So there are hundreds and thousands of types of oscillations. But out of all the cases, this right here is a very special case, which brings us a lot of interest into this topic. Like there is a lot, just because we follow this equation, we get to see a lot of interesting things. Okay. So this is called as a simple harmonic motion. People are asking, the force disappears in the middle. No, in the swing, the force is always there. Sumant is asking, in a swing, the force disappears in the middle. No, the force is always there. We will talk about all the things later, guys. Let's. I just wanted to introduce the importance of simple harmonic motion being like this: the force proportional to minus x, where minus is indicating the force is always restoring, and x is the force which is acting like the distance from the mean position. Can we give an example? Can anybody give an example that right out of your mind? Is there an example where it is following, where the system is following f proportional to minus x? Is there anything right out of your head? No? Nobody? I can give you an example. A guitar
Pendulum, sir.
string. Ganesh gave me the example. Yes.
So pendulum.
Pendulum also, we will talk about the pendulum because pendulum has a different property. We will talk about it. Take a spring block system. This is where the spring's natural length is. Like this is a natural leveling condition. I move the block forward by a distance x. We all know the spring expands, and we all know it creates a force kx in the direction backwards. So F, the restoring force, can be written as minus kx. So yes, a spring block system is definitely an SHM. I can gladly say that the spring block system is definitely an SHM. Clearly observe, guys, this is an interesting thing. But even when it is compressed also, this time, clearly observe, x is a negative value, force is acting positive now. Anyway, the point is force is always opposing the x value. That's it. If you're going into the positive, force is negative. If you're going into the negative, force is positive. And you clearly call this as a restoring force. Don't ever forget this point. We call this as a restoring force. Okay. Guys, I just have a doubt. I'm not talking about SHM. I'm just asking a question. When I said f equals to minus kx, it is SHM. So definitely there is an oscillation. When I said f equals to minus kx cube, looks like an oscillatory motion because minus is there. So there is a oscillatory motion for sure, minus kx cube. But my question is, can this be an oscillatory motion, minus kx square? Anybody has an argument regarding this? You please tell me.
It will be, sir, because minus is there, so there'll be no problem.
But that is where you're wrong. When you're going on to positive x values, the force is clearly acting backwards. No problem. But when I go into the negative x, put a negative x in this thing. Negative
Okay,
x
sir.
square is a positive value. So the overall thing again becomes negative. You see that, Aniket?
Yes, sir. So we can put it like a rule that the power should be odd.
Exactly. That's it. As long as you have an even power, like f equals to minus kx power 4 or minus kx power 6, they are all not oscillatory motions at all. They're not even oscillatory motions because the force direction is always negative there. X square can never be positive. Sorry, x square can never be negative. X square is always positive. So force is always negative. Force it cannot be always negative. If it is negative here, if it is negative here, there's no point. Force has to be negative sometimes and then positive, and then negative and then positive. That is how it's supposed to work. Look at this case in a spring block system. When x is positive, force is negative. And when x is negative, force is positive. So that is how it works. So this is how you need to clearly understand. Whenever there is force proportional to minus x, minus kx cube also works because x cube can be negative and positive. Minus kx power 5 can also work. Like Aniket said, all the odd terms definitely work, but all the even terms don't work. But it makes a lot more sense when once we really get into this topic. As we jump into this topic, things will start making more and more sense to you. Okay. Now, let's get official completely with SHM. From this point onwards, I'm only going to talk about SHM, simple harmonic motion. That's specific special case only. We're not going to talk about all the previous cases where there is oscillation and not non-oscillatory, periodic, non-periodic, and there are other things. We're not talking about all those things anymore. We are strictly talking about simple harmonic motions from this point. So when it comes to a simple harmonic motion, obviously there is a thing called a mean position. Okay, and whenever there is an oscillation, there must be a positive extreme. The body goes to a point, it definitely stops there, and it comes back. And similarly, whatever the positive value that you have, the screen sharing has stopped for some reason, I don't know. Let me share it again. So when I'm talking about SHM, there is a mean position for sure. There is a positive extreme position, and there is a equally negative extreme also, because the force is completely symmetrical. Like you don't really see any difference when it's going on to the positive side and when it's going to going on the negative side. Just like a spring, the spring doesn't behave different when it is expanding or when it is compressing. It is exactly behaving the same way when it is expanding and when it is compressing. So if there is a specific positive extreme, there must be a specific negative extreme also. So these values are called as amplitude. The value is called as amplitude. The maximum displacement from the main position it goes is called as an amplitude. Again, some doubt. If you, even then it can be oscillatory than SHM. What, I don't understand. So if you have a doubt, please raise your hand and ask. Okay. The plus value, the plus A is called as an amplitude. Yeah, minus A is also an amplitude. The value A itself is called as an amplitude. Okay. So mean position, amplitude, and then what do you need to know? What else do you need to know? There are other terms, but we will learn these things over time only. We don't talk about these things immediately. There's a thing called time period. Of course, you know what time period is, but what it is exactly, what it exactly means when it comes to a simple. Why don't we look at it? Can somebody tell me what exactly is the time period? I'm starting at mean position. At what position, I mean, at what point do you call it as time period? It started here, let us say. Aniket, where does it start and where does it have to end so that you call it as a complete time
So when
period?
you come back at the second time,
Why is it a second time?
so because you have to go this side, then again the other side, and then come
So
back.
you start here, you go in this direction. Guys, I'm drawing it like this. It's not, it doesn't mean the body is coming down and drawing like this. I can't draw all the lines on the same line. So you get confused, right? So I draw it like this. The body is going there and it is coming. But just because it has come to mean position, we are still not calling it as a full time period, because it is still going in the opposite direction now. Goes to the negative extreme and coming back. So from this point onwards, again, it repeats its motion. Clearly observe. It goes and comes back. So that is one full motion again. From this point, it goes, comes back. So this whole specific thing is one time period. This whole thing is a one time period. This whole thing is a time period. So to put it, a body has to start at the mean position, goes to the positive extreme, come back to the mean position, goes to the negative extreme, come back to the mean position. The whole thing is called as a time period.
So one small doubt.
Yeah.
So oscillation we defined as to and fro motion, right? Then here we should take in that way only.
What way?
So that it goes to a point and comes back. That's it.
Yeah. So you can understand this whole SHM motion like this, or you can simply look at the SHM like this also. This is mean. Let us say you started at negative extreme, you go cross the mean and come back. This is also one time period. It might confuse you, but look at it. The distance traveled is completely the same thing. It's not at all different. It traveled
Okay, sir.
A. Like clearly observe, it traveled A, then A, then A, and then A. So it traveled 4A here. The same thing also here. It traveled, let me take another color. Why not? It traveled A, then A, and then A. So you can defining a time period, people simply use the definition like this, but you can happily use this also. For the time taken for the body to start at the negative extreme and come back to the negative extreme. Yeah, you can simply say that is a time period also. Or you can say this also, like body for time taken for the body to start at the positive extreme, go and come back. This is also one time period. Or you can say the mean position, positive extreme, negative extreme, and the mean is also time period. You can call it in all the ways and all the
So
directions.
this is valid only for HHM, right, sir?
Yes, we are talking about a very, very special, a neat, simple case. The SHM is such a beautiful case. The reason why I'm calling this as a beautiful case, there is a lot of reasons. Okay, I'll talk about all the reasons. I'll talk about velocities. I'll talk about accelerations. I'll talk about all the plenty things for sure. But the reason why I'm calling is this topic is going to be the foundation of the topics of waves, sound, wave optics, and then alternating current. All these second year topics are strongly based on this topic. Okay, so this is very important. Remember the video that I've made on Instagram, sorry, not Instagram, on Facebook, not Facebook, YouTube. Phase difference, there is a word called, there is a video where I made it about a phase difference. I think you might have to watch the video not just today, maybe tomorrow, let's just say. Okay. We will talk about phase difference. All these things are going to be the foundation of the future topics that we're going to learn. So that is why I'm stressing it so much. Okay. Yeah, the one with the noise cancellation video. Yes, I mentioned that. Mm, so I think this introduction is good enough for you people. Try to look at this SHM a little more. Why don't you people try to go through the textbook of HC Verma once? Let me go take you to the topic. Mm, yeah, we are here. You don't really have to go into the depth. Let's just look at the basics of it in the first page. The first page itself, he simply talks about what is a restoring force and how a body needs to oscillate and all. I didn't really talk about all the mathematics or the depth of the topic. I just clearly like introduce the topic. So all you have is a very basic thing. Read this page, and this page is also fine if you want to, but no, you don't really have to do it. Tomorrow we will be talking about all the equations and how things are working. So let me end this topic just by talking about the force itself again. So force equals to force proportional to minus x, r. We will be talking about the spring forces, so we can write it as minus kx. So the acceleration is, mass into acceleration is minus kx. Acceleration equals to minus k by m into x. So guys, please remember this statement also. It's not just the force, the acceleration is also proportional to minus of displacement. This is also a very important statement when it comes to simple harmonic motion. It's not just the force that is proportional to minus x, it's the acceleration. Since we are going to talk about accelerations and velocities a lot in this topic, so this is also an important way to do it. We will talk about this thing later, what exactly this k by m means. Can somebody guess what this k by m means? What do you see in that thing when you write, like this is an acceleration, everyone knows this is displacement. Let me talk about this thing. This quantity right here, k by m, has a practical significance. Let me talk about the practical significance. This k value is a spring constant. What exactly spring constant does? It tells you how strong the spring is. So clearly when you're talking about k, you're talking about how restoring the medium is, like the restoring capacity of the spring. Take a very smooth spring, take a very strong spring. Which one is more restoring? So we are actually putting the capability of the restoring capability of the body or the system into the equation. And when we're talking about the mass, we are talking about inertia. There is a very important reason why I'm stressing it so much. So these two terms are actually talking about the restoring capability and inertia of the system. There is a very important reason why I'm stressing it. You'll understand it. So in this equation, we will get to learn that also. We will talk about these things tomorrow. Once we get into some clarity, we will definitely talk about them. That's it for today. Any doubts just regarding the class today? Just regarding the class, I'll just stop the recording, then we can talk if you have any other doubts. Just regarding the class, if you have any doubts, please let me know. Bungee jumping, is it an SHM or not? You will be mature enough to answer it yourself. So we'll tell me that. In bungee jumping, you don't go down and then go up and come back. So that should answer your that should answer your question. In bungee jumping, you start at some point, you go there and stop, right? So it's not really exactly SHM. Any more doubts, guys? Raise your hands before I stop. Nope. Nothing. So yeah, let me stop the recording first. Thanks so much and bye bye.